Okay, and I will share my screen. Okay, can you see my screen? Can you hear my voice?
Yes, Doctor.
Okay, thank you for the response. Okay, so last week we have learned about the amplitude shift keying, which is digital modulations with the analog carrier, where we do the modulation with analog carrier so that we can produce an analog signal that can be transmitted over the wireless medium. Okay, and we have learned that ASK is a type of digital modulations that will change the amplitude of the carrier in accordance with the digital input variation. Okay, so maybe before we continue our lecture session, we can refresh again what we have learned in the previous week. Okay, so I make a blank slide here so that I can make a simple drawing to you. So where are we now actually? Okay, so again I will repeat again my favorite picture about the transmitter and receiver. Okay, so this is the channel. Okay, okay, so now we have a digital input. Okay, now when we do the ASK, amplitude shift keying modulation, we are actually having the input of digital. Okay, we have digital input. Sorry, so we have digital input with logic 101010, and we want to transmit this signal across the wireless medium. So when we want to transmit in the wireless medium, we need to convert the input into electromagnetic waves that is suitable for transmission. Okay, and the frequency that we want to use is higher frequency, which is in the range of radio frequencies. Okay, so what we do is we're gonna do the modulation with analog carrier. Okay, we're gonna modulate with the analog carrier. So analog carrier modulate with digital input data. Okay, so this modulation will change the amplitude characteristic of the carrier in accordance with the digital input variation. So our digital input has only two possibilities, whether logic 0 or logic 1. And this variation will change the amplitude characteristic of the carrier, and we're going to produce a waveform, what we call as a ASK, amplitude shift keying. Okay, and then when it arrives at the receiver, okay, when the signal arrives at the receiver will do the process of demodulation. Again, we might also use the analog carrier to do the demodulation process, okay, and to produce the digital output. Okay, so in this case, you're going to see later that this receiver has the ability to do the demodulation either with the carrier information or without the carrier. If we use the carrier information to do the demodulation process, we call it as a coherent detection. And if we don't use the carrier information to do the demodulation, that means it is a non-coherent detection. Okay, so there's also another issue in the receiver, that there might be possibility that the receiver will do the error. Okay, Error means that when we transmit, for example, 101010, suddenly the receiver interprets it as 111010. So this is example, and you're going to see that this is the bit error produced by the receiver. And we have the parameters probability of bit error. Okay, the parameter that shows how much is the probability that the receiver will do the error. Okay, so ASK, amplitude shift keying, we have learned that the general equation for the ASK is this one, 1 plus VMT multiplied with VC cos omega CT. Okay, so VMT is the input. So the input now has only two possibilities, logic 0 or logic 1. If it is a logic 1, that means we need to replace VMT with positive 1. If the input is logic 0, that means we need to change VMT into minus 1. Okay, so what happened? So if the input is logic 1, okay, we change VMT with plus 1. Okay, so we're going to produce output 2 times VC cos omega CT. And if the input is logic 0, so we will change the VMT with minus 1. So therefore, it's going to produce 0 output. So 0 output here means no output, empty. Okay, that means it's like the system is switched off, something like that. Okay, so there's no output. Okay, so this ASK is also known as the on and off keying. Okay, because of these characteristics, when the input is logic 0, it's going to produce 0 output, no output. So it is like a switch, on and off switch. Okay, so if you see from this slide, we have the input 1010. Okay, so whenever there's a input logic 1, we're going to produce a output here. Okay, sine wave. And if it is a logic 0, there's no output. Okay, nothing. And this is the waveform, and also the spectrum, and also the bandwidth. Okay, if you see from here, we have seen this. So this is the input VMT 1010. Okay, input VMT 1010. And how does the ASK signal looks like? So it looks like this: sine wave, off, sine wave, off, sine wave, off. Okay, so switch on, switch off, switch on, switch off. So this is the ASK, also known as the on and off keying. Okay, what about the frequency spectrum? So if the input signal is up to the 5th harmonics, for example, okay, for example, we have the input up to 5th harmonics, okay, up to 5 FM. That means the bandwidth gonna be 2 times the input frequency. Okay, so if the input is up to 5 FM, that means it is up to the 5th harmonics, and it's gonna produce the bandwidth of 10 FM. If it is up to 6 FM, for example, we're gonna produce 2 times 6 FM. Okay, so the general equation is 2 times x FM. Okay, if it is a 1 FM, so 2 times FM. So if it is up to 5th harmonics, that means 2 times 5 FM. Okay, so it is 2 times the input frequencies. So this is the bandwidth for ASK. Okay, and this is the OOK multiplier circuit. So this is the modulator inside the transmitter. Okay, so this is the modulation process inside the transmitter, where it uses the multiplier circuit to produce the ASK. Okay, so there are many methods available in the practical world. One of it is to use the multiplier circuit, where we multiply the input with the analog carrier to produce the ASK signal. Okay, so this is like a switch on, switch off, switch on, switch off, and so on. based on the input. And remember, we only have two possibilities of the input, either logic 1 or logic 0 from the input. So this is more easy compared to the analog system where we have infinite shape of the input. Okay, so this is the ASK modulation process to produce ASK signal or OOK signal. Okay, ASK also known as the OOK signal. And then this is the demodulation circuit, the demodulation block diagram within the inside the receiver. Okay, so this is what happened in the receiver. Okay, so in this slide you're gonna see that we are using coherent detection. That means we are using the carrier information to do the demodulation process to produce the original output signal. Okay, so the word coherent here means that we are using the carrier information, okay, to do the demodulation in order to produce the original signal at the output. Okay, there's also another type of there's also another type of detection, which is what we call as a non-coherent detection. Okay, for non-coherent detection, we are not using the carrier information to do the demodulation process. Okay, so when we use a coherent, that means we need to use the carrier informations. We will combine it. Okay, what we will do is that we will do the multiplication process mathematically to produce the upper sideband and also the lower sideband. If you remember about the balance modulator, what happened when we multiply two inputs, we're going to produce upper sideband, higher frequency, and also the lower sideband signal, which is a lower frequency. So when we produce two types of frequencies, then we can select either one of it using the filter. So in this case, we are using low pass filter to select the low frequency signal, okay, which is the LSB, and remove the high frequency signal. Okay, and we're going to produce the original output. Okay, so the output here is going to be either digital or analog. Okay, if the input is digital, that means we're going to produce the digital output. Okay, if the input is analog, that means we need more process to produce the analog output. Okay, remember we have the flexibility to produce either digital or analog output. Okay, also non-coherent, which is non-coherent, we can use a envelope detector. So this is the name of the non-coherent detector, also known as the envelope detector. Okay, this is a using a synchronous detection. This is a synchronous detection, and for the non-coherent we can use the envelope detector. Okay, so this is one of it. Okay, there are many other types of the non-coherent detection process, okay, which is a non-synchronous detection. So probability of bit error, we have learned about this, how to calculate the probability, okay, that error will happen in the receiver. Okay, so it is equal to PBE, probability of bit error, is equal to 1/2 complementary error function of square root of EB over 2 and 0. Okay, and in order to find this, you need to use the error function table or complementary error function table, which will be given in the exam. Okay, so before the COVID pandemic, we give the table, but since now we are going to do the online exam, so we are not include in the question. So you need to find it in the notes. Okay, in the lecture notes. Okay, so how to find the error function? Okay, So we have there are two tables. The first one is the ERF table or error function table. Okay, we have the x versus this is the input, x input, and the numbers over here. Okay, the numbers over here is the output. Okay, the probability of bit error. So for example, if the input is 0.40, okay, so it's gonna produce error function 0.42839. Okay, the ERF of 0.40 is equal to 0.42839. Or if the x, this is if x equal to 0.40, so you're going to produce ERF equal to 0.42839. Okay, and if x equal to 0.49, so the ERF, okay, ERF is equal to this one, 0.51167. Okay, so this is how we read the table, okay, based on the value of input x. Okay, for example, if the input is 2.47, okay, 2.47, okay, for example, x is equal to 2.47, so the ERF error function produce 0.99952, okay, and so on. Similar with the complementary error function, ERFC. Okay, so ERFC, again, if the input x is 0.40, okay, that means the ERFC is equal to 0.57161, 0.57161, okay. Or if the input is 0.49, okay, so the complementary error function is equal to 0.48833. Okay, so it is important for you to understand how to use the table. Okay, so let's do the example. Okay, so let's do the example. Given EB over N0 is equal to 0.32, find the probability of bit error. Okay, EB over N0 is the energy bit over noise power spectral density, which is 0.32. Okay, so based on this value, find the probability of bit error of ASK using coherent detection. Okay, using coherent detection. So this is the equation. Okay, so what we need to do is we can put inside the equation 0.2 inside the equations. Okay, so from these equations, okay, we separate EB over N0, okay, EB over N0, and then we put inside the equation 0.32. So it is 1 over 2 ERFC square root of 0.16, which is 1 over 2 ERFC 0.4, okay, 0.4 or 0.40. So now, if you see from this example, okay, complementary error function of 0.4. So in this example, it used the ERF table at the beginning. So you have two options. Either you want to refer to the ERF table or you want to refer to the ERFC table. Okay, so if you refer to the ERF table, which is the first table, okay, ERF 0.4, okay, 0.4, if you see the first table, error function table, 0.40, which is this one, okay, so you're going to produce 0.42839, okay. Or if you refer to the second table, complementary error function table, 0.40 will produce this value. So this is a direct answer, okay. So if you ask me, better to use the second table because this is a complementary error function table. You can get the answer directly. Okay, but this example wants to show you, if we use the first table, what we should do actually. Okay, so if you use the first table, which is the error function table, so you need to minus with 1. Okay, minus the value with 1 in order to find the complementary error function. Okay, so based on the first table, ERF 0.4, you get 0.42839, and then complementary error function is equal to 1 minus the value, so we get 0.57161. So this actually you can get from the second table. Okay, second table, if you see from here, second table, this one, complementary error function table, you can get the value directly. Okay, so of course using the second table is more convenient. We can straight away get the answer. Okay, so therefore using this value, okay, using this value, okay, so ERFC of 0.4, we get 0.57161. So it is not finished yet, so we need to multiply it with 1 over 2. So we get 0.2858. Okay, so this is the probability of bit error in the receiver for EB over N0 equal to 0.32. Okay, for different value of EB over N0, it's going to produce different value of probability of bit error. Okay. Okay, so this is the probability of bit error for coherent detection. Okay, if the receiver is using a coherent detection method, that means the formula to find the PBE is based on these equations. Okay, remember this is for coherent detection. Coherent detection at the receiver. Okay, coherent detection at the receiver. And what if the receiver is using non-coherent detection? What happened? Okay, so if the receiver is using non-coherent detection, we can use this equation. Okay, for non-coherent. So for non-coherent detection, we can use this equation. If you see from here, it is using the exponential equations, which is not based on the table. You can directly use your calculator. Okay, so based on this example, so this is for non-coherent detection at the receiver. Remember, if the receiver is a non-coherent type, non-coherent means that we are not using carrier information to do the demodulation process. Okay, so given the example, EV over N0 is equal to 1.11, find the probability of bit error. Okay, so using a non-coherent, so you can use these equations. Again, we rewrite the equation to separate the EB over N0 so that easy for us to do the calculation. Okay, so from here, okay, see that 1 over 2 exponent power of minus 1 over 2, 1.11. Okay, so you get 1 over 2 exponent minus 0.555. So from here, you can use your calculator. Okay, please open your calculator. Okay, so exponent using my calculator, Casio FX 570MS, it is shift ln. Okay, you can press shift ln and then you can put inside minus 0.555 and you will get 0.5741. Okay, 0.5741 from the calculator, and you can multiply with 0.5, half of it, so you get 0.2870. Okay, so therefore you are going to find the probability of bit error without using the table. Okay. So any question you want to ask, please ask question regarding this. So for your information, we have asked these kind of questions in the previous semesters. Okay. Where we give the EB over N0, find the probability of bit error. So the thing is, the key point here is that you need to understand how to use the table and also how to use the equations for the non-coherent. Okay. So previously we asked for coherent detection where we give the table, so students need to use the table. Okay. So if there's no question to ask about this, I will move to the next topic, which is, okay, so if there's no questions about this, I will move to the next topic, which is about frequency shift keying, this one. Okay, so frequency shift keying is similar with the frequency modulation in the analog system. Okay, similar but not the same. Okay, so now the issue is we have the digital input and we want to transmit the signal as analog. Okay, what we do is we modulate the input with analog carrier, and this process change the frequency characteristic of the carrier in accordance with the digital input variation. Okay, so you see from here the general equation of frequency shift keying is equal to Vc cos 2 pi Fc plus Vmt delta Ft. Okay, so this is the general equation for Vfsk. And the thing that will change is this one, Vmt will change according to the input. So if the input is in logic 1, Vmt gonna be plus 1. Okay, if the input is logic 0, that means Vmt gonna be minus 1. Okay, so what happened is that you see that if the input is logic 1, okay, if the input is logic 1, so therefore Vmt gonna be positive 1. Okay, so you're gonna just need to change the Vmt into positive 1. So this is supposed to be just a positive, so you don't need to put Vmt over here. So it is actually 2 pi Fc plus delta F. So this is supposed to be Fc plus delta F. Okay, so you're going to produce a high frequency at the output for input logic 1. Okay, what about if the input is logic 0? That means you need to change Vmt with minus 1. Okay, so therefore this is Fc minus delta F. Okay, so this is supposed to be Fc minus delta F. Okay, Vmt we already changed into minus 1. So whenever there's an input logic 0, okay, the output gonna be low frequency at the output. Okay, and from here we can calculate the bandwidth based on the Carson's rule. Okay, based on the Carson's rule, which is 2 times delta F plus B. So B here is the highest frequency of the input. Okay, B here is the highest frequency of the input. So we are calculating the bandwidth based on the Carson's rule. Okay, and this is the modulation process in the transmitter to produce the FSK signal. Okay, so if you see the picture above, okay, picture A, you see that here we have a digital input 101. Okay, so this will be supplied to the first balance modulator, the first balance modulator. Okay, And the input also supplied to the second balance modulator, but before that we have the inverter over here which will inverse the input. So whenever there is an input logic 1 will be inverse to logic 0, input logic 0 inverse to logic 1, input logic 1 inverse to logic 0. Okay, so this is supplied to the second balance modulator. Okay, and each of the balance modulator is also supplied with the oscillator with different frequency. So frequency oscillator frequency F1 supplied to the first balance modulator, oscillator with frequency F2 supplied to the second balance modulator. Okay, so what happened is that over here, so the in this example, the first oscillator has higher frequency compared to the second oscillator F2. Okay, so what happened? So when we supply to the balance modulator, it will do the process of multiplication in time domain. So what happened is 1 multiplied with sine wave. So oscillator is generating a sine wave, so it's going to produce a signal. Input logic 0 multiplied with anything is going to produce 0 output, and then input logic 1 produce sine wave at the output. So this is like a ASK. Okay, this is like a ASK process. Okay, and then for the second balance modulator, we are multiplying the sine wave F2 frequency from the oscillator with the input. Okay, so 0 multiplied with the sine wave, so there is a 0 output. And then we have input logic 1 multiplied with oscillator frequency F2, we're going to produce output sine wave. Remember, F2 has a frequency less than F1. So that's why you're going to see that the sine wave is a single sine wave here compared to the 3 or 4 sine wave produced by first balance modulator. Okay, so this is because F2 is smaller than F1. Okay, frequency F2 is smaller than frequency F1. Okay, so that's why you're going to produce this one. Okay, and then input logic 0 produce 0 output. Okay, so now it is passed through the summer to sum up the output from first balance modulator and also output from the second balance modulator. So what happens? So we're going to plus this signal and also this signal. Okay, so you see that the first it's going to produce the output. Okay, we just add up both of it. Okay, so it has a high frequency signal, low frequency signal, high frequency signal. So this is actually representing the input of 1, 0, 1. Okay, similar with the input. Okay, so input logic 1 produce high frequency output, input logic 0 produce low frequency output, and so on. Okay, and picture below is using similar with picture above. Okay, this is only a single block diagram here using a frequency modulated oscillator where we have different kind of circuits over here. Okay, so you see that from here is logic 1, logic 0, logic 1. Okay, so you're going to produce a high frequency, low frequency, high frequency. Okay, so this is the FSK. And for FSK, the low frequency is what we call as a space frequency, Fs. And high frequency, you see that the ripple is close one another. This is a high frequency signal. It is called as the Mach frequency, Fm. Okay, it's not the modulating signal, it is a Mach frequency. This is just a term used to represent the low frequency and also the high frequency. Okay. So this is the waveform for the ASK. Okay, make sure you also know how to sketch the waveform for ASK, for FSK, and also the PSK. Okay, previously we have asked this kind of questions where we give the input logic 01010, produce the output waveform. Okay, so the output waveform is in the form of sine wave, but you need to know that for FSK, the output has different kind of frequencies. Okay, for high frequency, you need to do sine wave with the ripples are close to another. Okay, untuk FSK ini, untuk frekuensi yang tinggi, dia punya bentuk gelombang itu adalah rapat-rapat kerana dia high frequency. For low frequency, the ripple is further away from each other. Okay, untuk frekuensi yang rendah, dia punya bentuk gelombang itu jarak-jarak. Okay. And this is the waveform of the ASK. We have seen about this. Okay, for input logic 1010, and it's gonna be produce FSK output like this. Input logic 1 high frequency, input logic 0 low frequency. So you're gonna see that the difference low frequency is that the ripples are further away from one another. Okay, and then here is input logic 1 and so on. Okay, so what about the frequency spectrum for the bandwidth? So for the bandwidth, you see that here, if the input is up to the 5th harmonics, that means the equation for the bandwidth is based on the Carson's rule. So 2fm plus x delta f, sorry, xfm plus delta f. So if it is up to 5th harmonics, that means we need to add 5fm here because the input is up to 5th harmonics plus delta f. Okay, so if you see from here, if we have up to 10 harmonics, for example up to 10 fm, okay, that means we're gonna need to use 2 times 10 fm plus delta f. Okay, so this is how we calculate the bandwidth, okay, based on the Carson's rule. Okay, and this is the generation of, sorry, this is the detection process at the receiver. Okay, this is the detection process at the receiver. So the first one is coherent detection. Okay, coherent detection means we are using the carrier information to do the demodulation process. Okay, we use a carrier information to do the demodulation process. So this is a coherent. Okay, and you see that this is a FSK. So FSK put inside the power splitter will split the input with different kind of powers. Okay, and then we multiply it with the carrier. So after we multiply with the carrier, it's going to produce a USB and also the LSB frequency. Okay, and we can select the low frequency signal using the low pass filter to select the low frequency and remove the high frequency. Okay, and then here is the comparator. So we can produce the output here as a digital output logic 101010. Okay, and for picture B, this is a non-coherent detection where we are not using the carrier information to do the demodulation process. Okay, instead we are using a bandpass filter, 2 bandpass filter to select space frequency and also mark frequency. Okay, and then put inside the envelope detector, and then it's gonna produce a DC output, DC voltage output. So this DC voltage output will be put inside the comparator to compare whether this is a logic 1 or logic 0. Okay, comparator is to change the to convert the DC input, okay, input with a voltage, change it into logic 1 or logic 0. Okay, so you're going to produce a logic 1 or logic 0 output. Okay, 0 1 0 1 0 1 and so on. Okay, and then what about the probability of bit error for FSK? Okay, probability of bit error for FSK using a coherent. Okay, if the receiver is using a coherent detection, how to calculate the probability of bit error? So if you see from this equation, the equation is the same as ASK. Okay, sama seperti ASK, same as ASK method. Okay, and also for the non-coherent, okay, we are using this equation. PBE equal to 1 over 2 exponent power of minus EB over 2 and 0. Again, this is for non-coherent detection of FSK. And this is similar with the ASK. Same equation. So FSK and ASK are using the same equation to calculate the probability of bit error. Okay. Okay, the next topic is phase shift keying. Okay, the next topic is phase shift keying. So this is another type of modulation. This is another type of modulation which is similar with the PM, phase modulation in the analog. Okay, dia adalah setara dengan phase modulation dalam analog. Okay, and phase shift keying means that it is a modulation process that change the phase of the carrier in accordance with the digital input variation. Okay, so again, ASK, FSK, and also the PSK, they have different variation types. Okay, what you see before ASK, so previously we have seen about ASK, FSK, and also the phase shift keying, PSK. PSK is a modulation process that change the phase characteristic of the carrier in accordance with the digital input variation. Okay, and remember, all of these three modulation type, ASK, FSK, and PSK, they have different types of variations of each modulation type. They have a big family. Okay, so the way we write the term for the modulation, so this is M, sorry, okay, wait, M ASK, M FSK, M PSK. What is M? Okay, M is the number of symbol. Okay, M is equal to 2 power of n. N is the number of bit. Okay, N is the number of bit. Okay, this N is the number of bit. Okay, so you see that N, so M, this M, normally the maximum would be 256. Okay, the maximum normally is 256. 256 symbols. Okay, for the practical modulations type that we use in the real world, okay, it is normally up to 256. Okay, so we have if m is for example, if the number of bit is 1 bit that we use, okay, if here is using k, so this is also a number of bit. So if the number of bit is 1, okay, if the number of bit is 1, that means the number of symbol that we're going to produce is 2 power of 1, which is equal to 2. Okay, 2 symbol, what is it actually? 0 and, okay, 0 and 1. And this is what we call as a binary. Okay, the name is BPSK. Okay, so 2 PSK is known as BPSK. This is just a term, binary. So the word binary, you know, binary, we have input logic 1 or input logic 0. Okay, and there are many other types, okay, similar with the ASK and the FSK. Okay, so now since we are talking about PSK, so there is also 4 PSK. Okay, so this is one of the one of the famous modulation type. So this is if you ever heard about QPSK, Quadrature phase shift keying. There's also 8 PSK. Okay, I forgot the name. Okay, and so on. Okay, there are many other levels of modulations. Okay, so you see that each of these, ASK, FSK, and PSK, they have many levels of modulations. Okay, so normally in the real world we are using a high level of modulation. So the higher the number of m, that means we are using a high level modulation. Okay, so there's a pro and cons about using the high level modulations, where we can transmit many symbols. Okay, we can have a higher data rate. Okay, and also the drawback would be the bandwidth. Okay, so there's a give and take about using the high modulation scheme. Okay, so for your syllabus, okay, for PSK, we are learning up to BPSK. Later you're going to see about Qualm. Later we have another one, what we call as a Qualm. I will show you later. So for PSK here is in this slide is up to 2 PSK, which is binary phase shift keying. Okay, BPSK. So BPSK has 2 symbols, either logic 1 or logic 0. So since we have two symbols, logic 1 or logic 0, so each symbol is separated by 180 degree of phase. Okay, so we're going to see about that later, about the phase shift. So let's see the generation of BPSK signal inside the transmitter. How we want to generate the BPSK signal. Okay, so this is in the transmitter. Okay, so you see that we have the binary input, logic 1, logic 0, 1, 0, and so on. Okay, and this is put inside the level converter, okay, to produce from unipolar into a bipolar signal. So bipolar signal means that we have positive and negative voltage polarity. Okay, and put inside the balance modulator. So this will do the multiplications with another signal, which is sine wave. Okay, so the output of the balance modulator, so you see that we have positive and negative. So the output of the balance modulator, remember balance modulator will multiply the inputs. Okay, so since we have a sine wave here multiplied with positive or negative voltage, so what happened is that assuming that the level here is positive 1 and also negative 1, if we assume that it is a positive 1 and negative 1, that means we're going to produce positive sign, okay, positive sign omega ct, or negative sign omega ct. Okay, so we're going to produce positive sign or negative sign, the output of the balanced modulator. And then bandpass filter will select either of these, and then we can transmit to the medium. Okay, so how does the positive and negative sign looks like? Okay, so sine wave, as you know, that sine wave is like this. Okay, so this is the sine omega ct. Okay, this is a normal sine. What about negative sign? For negative sign, we start from here like this. It is inverse. Okay, this is the negative sine omega ct. Okay, this is negative sine omega ct. So bandpass filter will filter out the unwanted signal, and then we transmit to the medium. Okay, then receive by the receiver. Okay, so this is at the receiver side. So the receiver side, okay, before that. So what we will transmit over here, okay, what we will transmit over in the medium, it is either sine wave, positive sine wave, or negative sine wave. Okay, so we have two possibilities that we transmit at one time. Okay, pada satu-satu masa kita akan hantar salah satu, either one sine wave or negative sign. Okay, to represent each bit. Okay, so in the receiver, okay, so the receiver now receive the PSK. So the receiver receive either this is a positive sign or negative sign. So if the input is positive sign, we know that it is actually logic 1. If the input to the receiver is negative sign omega ct, that means we already know that it is actually a negative, a logic 0 input. Okay, so I repeat again. So positive, okay, so positive sign to represent logic 1, negative sign to represent logic 0. Okay, again this is from here, from this, and you see that here. So logic 1 represented by positive voltage, logic 0 by negative voltage. So that means for the output logic 1, it is actually we will transmit positive sign. For the input logic 0, we will transmit negative sine wave. Okay, so at the receiver, we either receive positive or negative sign to the receiver. Okay, then put inside the balance modulator to remove the unwanted frequency signal, and then we put inside the balance modulator. Okay, so since we are using the carrier information, so this is a carrier coherent detection, where we will again multiply the input with the carrier. Okay, we multiply the input with the carrier, which is sine omega ct. Okay, so sine and sine, okay, sine omega ct multiplied with sine omega ct. Okay, so remember, balance modulator will do the process of multiplication. Okay, so when we multiply sine and sine, we're gonna produce upper sideband and also the lower sideband. Okay, upper sideband and lower sideband. Okay, and then we can use a low pass filter to select the low frequency and remove the high frequency. Okay, and then put inside the level converter to convert the signal into to convert the voltage pulses into a digital data. Okay, 1010. Okay, so level converter here. So since we are using the bipolar, so we are using a level converter to change it to unipolar. Okay, unipolar at the output. Okay, so unipolar output 1010. So this is only a single polarity positive voltage at the output. Okay, so we have asked this question previously in before the COVID pandemic, and we have asked this question where we give the input, and the students need to find the equations for the output. Okay, so this is the equation. This is a simple equation for the output of a balance modulator. Okay, sorry, this is this is the equations for the detection process at the receiver. Okay, so remember here we receive input either positive sign or negative sign. Okay, and then it is put inside the balance modulator where we multiplied with sine wave. Okay, so if you see from this equation, okay, so from these equations you see that we have input over here. Okay, remember if we receive sine omega ct, okay, if we receive sine omega ct, it is actually representing by logic 1 from the transmitter. Okay, so at the receiver we want to demodulate this signal. So we put inside the balance modulator, we multiplied with the carrier, sine wave, and then we produce sine square. Remember sine square, we're going to produce high frequency and also the low frequency output. Okay, so here if you see from here, it's going to produce a sine square. According to trigonometry identity, it is equal to 1/2 1 minus cos omega ct. So this is a high frequency component. Okay, so rearrange the equation, it is like this. Okay, and you see from here, this part is a high frequency component which will be filtered out by the low pass filter. Okay, it will be filtered out by the low pass filter. Okay, so this is the output from balance modulator, 1/2 minus 1/2 cos 2 omega ct. Okay, after we put inside the low pass filter, which is this one, low pass filter. Okay, low pass filter will only select low frequency signal and remove the high frequency signal. Okay, so the component 1/2 cos 2 omega ct will be filtered out. Okay, so the output of the low pass filter is only 1/2 positive. Okay, so since this is a positive value, so it is actually representing by logic 1. Okay, so let's look at another input to the receiver, which is if the receiver receives negative sine omega ct. So negative sign, we know that from the transmitter it is logic 0. Okay, if you see from the transmitter, you see that transmitter negative sign, okay, negative voltage, okay, negative voltage multiplied with sine, so you're gonna produce negative sign at the output of transmitter. Okay, so logic 0 input will be represented by negative sign. Logic 1 input at the transmitter will be represented by sine, positive sign. Okay, so here at the receiver, we are receiving negative sign, so this is actually logic 0. Okay, so the output of the balanced modulator would be input multiplied with carrier sine wave. So we multiplied in the balanced modulator is going to be sine square omega ct. Sine square omega ct, sorry, minus sine square omega ct, according to trigonometry identity, it is equal to minus 1 over 2 in bracket 1 minus cos omega 2 omega ct. So 2 omega ct is a high frequency component. Okay, and this is the output of balanced modulator. We have two components, high frequency and low frequency. Okay, and we're gonna put inside the low pass filter. What happens is that low pass filter will remove cos 2 omega ct. So therefore we produce the output of negative 1 over 2. Negative 1 over 2 is representing by logic 0 because the value is negative. Okay, so it is logic 0. Okay, so we have asked this kind of question previously. Okay, previously we gave the input, we provide the input either sine wave or negative sign in the input and then produce the output. Okay, it's very simple questions to produce the logic output. Okay, okay, so now this is the this is what we call as the truth table phasor diagram. The arrow diagram is what we call as the phasor diagram, and the dot diagram is what we call as the constellation diagram. Okay, so what is this actually? So if you see the first one, okay, the first one, picture A, table A, this is to show the relationship between logic number and also the output phase. Remember, we are learning about PSK, so it is about changing the phase of the carrier. Okay, so logic 0, okay, it is 180 degree out of phase, and logic 1 is 0 degree out of phase. That means no change of phase. Okay, so what is this actually? So if you see here positive sign, remember logic 1 is representing as sine wave, sine omega ct, whereas logic 0 is representing by negative sign. Okay, so you see that here for logic 1, there's no phase changes. The phase starts at 0 degree. Whereas for input logic 0, since we are producing negative sign, so we are actually inverse, so we are actually change the phase, inverse the phase by 180 degree. Okay, when inversion occurs, it is actually 180 degree of phase shift. Okay, so logic 1, we are still using a normal sine wave, but for logic 0, it is inverse. So the inversion means that here is 180 degree phase shift. Okay, so from this table, we can draw the arrow diagram or phasor diagram. Okay, so you see that logic 0 is 180 degree, logic 1 is 0 degree. So that means we have only two possibilities, 0 degree and 180 degree. So if you see from this phasor diagram, you see that we have a we have, this is what we call as a fourth quadrant diagram. Okay, we have four quadrant. So 1, 2, 3, 4. Okay, so if you see from here, this is for what we call for the for the x-axis, it is representing by sine. Okay, sine. And for the y-axis, it is representing by cosine. Okay, so for logic 0, okay, for logic 1, okay, logic 1 means that there's 0 degree. Okay, so 0 degree means it is at the x-axis towards the right side. If the input is logic 0, that means it is negative sign. So negative sign is over here, which is 180 degree phase shift. 180 degree means from 0 over here, okay, from 0 until 180 degree. Okay, 180 degree from the quadrant, from 0. If you move anti-clockwise, okay, anti-clockwise, so it is a 180 degree of phase shift. So 180 degree is towards the left side. Okay, so the arrow shows the left side. Okay, so this is the arrow diagram to show the direction of the phase. Okay, and then we have the third diagram, what we call as the constellation diagram. So this is a dot diagram to show the symbol of the PSK. So now we are using a binary phase shift keying. Remember, we only have two possibilities or two symbols only, either logic 0 or logic 1. That means we only have two symbols only. Okay, that because we are transmitting either sine wave or negative sine wave. Okay, so in this in this constellation diagram, since we have two symbols only, for logic 0, it is located at 0 degree, which is this one, and another one is for logic 0, which is located at 180 degree of phase. Okay, so this is 180 degree. Okay, so we have two dot over here. So this is to show the distance between two symbols. So both of these, especially for the constellation, we want to see the distance between the two symbols. So if the distance is further away, that means the interference among the symbols will be very small, and the error produced by the system will be smaller. If we go to high level modulations, okay, if you see later, we have high level of modulation where we have many dots in each of the quadrant. The more the dots, okay, the high chances that there's gonna be the chances of having errors is higher. Okay, so one of the usage of the constellation diagram is to see the distance between each symbols. And remember, the closer the distance among each other, that means the chances of error happens would be higher. Okay, so that one is we are not learning about that. That one is more towards the eye diagram, which will be learned in the digital communication subject. Okay, so you are lucky enough not to learn up to that point. Okay. Okay, so this is the waveform of PSK. Okay, the waveform of PSK. So remember, PSK, we have sine wave or negative sine. Okay, sine wave or negative sine. So you see that from here, this is if input logic 1, we're going to produce positive sign. Okay, and for input logic 0, we're going to produce negative sign. So negative sign starts from below, above. Okay, and then input logic 1, sine wave, and then negative sign, and then sine wave, and so on. Okay, and the difference here is 180 degree. Okay, 180 degree. So this is the BPSK waveform. Okay, BPSK waveform. And this is the waveform and also the spectrum and bandwidth. If you see from here, we have seen this graph. So logic 1, logic 0, input logic 1, logic 0, 1, 0, 1, 0. Okay, so you see that input logic 1, sine wave. Okay, sine wave. And sine wave, and then input logic 0 is going to be negative sign. Okay, and then input logic 1 is going to be sine wave. Okay, and then input logic 0 going to be negative sign, and so on. Okay, so the difference of phase is 180 degree between logic 0 and logic 1. What about the bandwidth? Okay, so the bandwidth of PSK is similar with the bandwidth of ASK, which is 2 times the input frequency. Okay, 2 times the input frequency. So if the input is up to 5th harmonics, that means the bandwidth gonna be 2 times 5 FM. If the input is up to 10 harmonics, for example, okay, that means the bandwidth gonna be 2 times 10 FM. Okay, and so on. Okay, dan seterusnya. What about the probability of bit error? Macam mana pula dengan probability of bit error for PSK? Okay, so probability of bit error for PSK is slightly different from ASK and FSK. So what's the difference if you see from this? From these equations. So this is the above equation is for coherent detection. Okay, so that means we are using the table. Okay, so PBE is equal to 1 over 2 ERF square root of EB over N0. So what's the difference? Okay, so there's no 2 over here. Remember for ASK and PSK we have 1 over 2 EB over N0. Now there's no 1 over 2. Okay, tidak ada nilai setengah dalam equation ini. Okay, so previously there's a EB 1 over 2 EB over N0. So now there's no 1 over 2. So that's the difference. Okay, and for the non-coherent PSK, okay, so it is based on the exponent equations. So 1 over 2 E exponent power of minus EB over N0. Again, there's no 1 over 2 over here. So that's the difference between PSK and also the ASK FSK. Okay. Okay, so if you don't have question about this, we can move to the next topic, which is this one. Okay, quadrature, amplitude modulation. Okay, so QAM is also considered one of the high-level modulation techniques, which is highly used in the modern technologies of 4G and 5G. Okay, we are using the Qualm modulation techniques. Okay, so Qualm is combination of ASK, amplitude shift keying, and also the phase shift keying. Okay, it is a combination of ASK and PSK combined. Okay, that means there gonna be amplitude variation and also phase variation at the output. Okay, maka sebenarnya akan ada perubahan fasa dan juga perubahan amplitude carrier. Okay, so these modulation techniques will change the amplitude and the phase of the carrier in accordance with the digital input variation. Okay, so this is one of the high-level modulation techniques which is widely used in the current system. Okay, so we're gonna see here example of 8 QAM and also 16 QAM. So for you, 8 QAM is important because previously we put this in the quiz, second quiz. Okay, so second quiz might use up there might be a few questions about 8 QAM. What is 8 QAM? So 8 QAM means that m equal to 8. Okay, that means we are using 3 bit, 2 power of 3. Okay, the number of bit that we use is 3. That means we have 8 symbols from 0, 0, 0. Okay, from if I put here 0, 0, 0, so 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So you see that we have 1, 2, 3, 4, 5, 6, 7, 8 symbols. Okay, so each of these are the symbols. We have 8 symbols. Okay, to represent, we have 8 symbols to represent each of the input. Okay, so that means our input is 3 bit, 3 bit, 3 bit. Okay, every 3 bit is 1 symbol. Every 3 bit of input would be 1 symbol. Okay, so what about 16 QAM? Okay, QAM, we normally pronounce it as QAM. Okay, so 16 QAM, for 16 QAM, m equal to 16. That means we are using 4 bit. Okay, we are using 4 bit. That means we're gonna have 16 symbols from 0, 0, 0, 0 until 1, 1, 1, 1. So we have 16 possibilities of input, and we're going to have 16 of symbols to represent the input. Okay, so this is one of the high level. So let's try this. I hope that I will try to explain to you so that you can have better understanding about this. Okay. Okay. So don't be stressed to look at this block diagram. Jangan stress bila lihat block diagram macam ni. Okay. So I hope. So before we continue, can I get your response? Are you still there? Can you hear my voice? Boleh dapatkan respon, pelajar?
Yes, thanks.
Okay, okay. Thank you for the response. So you are still there. Okay, that's good. Okay. Okay, if you see from this is a block diagram of 8 QAM transmitter. Okay, this is a 8 QAM transmitter block diagram. So you see that we have we are using 3 bit, okay, to produce a 8 QAM at the output. So the input here is 3-bit. Okay, you see that we have input 3-bit, which is classified as Q, I, and C bit. What is this? Q is the quadrature bit. Okay, Q is a quadrature. Okay, quadrature. I is the in phase. C is a control bit. Okay, so quadrature, in phase, control. Okay, so at the input, we will separate the input. Okay, Q will go to the Q channel. I bit will go to the I channel. And C bit, the control bit, will go to the both channel, I channel and Q channel. Okay, and then what? So you see that both I channel and Q channel have the 2 to 4 level converter. Okay, so both of these channel have 2 to 4 level converter. Okay, what is this actually? So this level converter to change input into to change the logic input into voltage output. So the term 2 to 4, that means you have 2 input, you're going to have 4 possibility of output. Okay, so you see that the input here, okay, each of the input to the level converter is either logic 0 0, okay, 0 1, 1 0, or 1 1. Okay, so we have 4 possibility of output, 4 possibility of voltage at the output. Okay, similar with the Q channel, the input gonna be 0 0, 0 1, 1 0, 1 1. Okay, so we are using 2-bit input to the level converter to produce 4 different levels of voltages. Okay, level converter ini akan menukar logic input kepada voltage output. Okay, so what are the voltage? Okay, so in this example, the output voltage from the level converter is given in table B. Okay, so in this example, for input 0 0, so 0 here is from the I or Q bit. Okay, if the input to the level converter is 0 0, it will produce negative 0.541 volt. If the input is 0 1, the level converter will produce output negative 1.307 volt. If the input to the level converter 10, it will produce, the level converter will produce output positive 0.541. And if the input is 11, it's gonna produce positive 1.307 volt at the output. Okay, so there are 4 possible output from the level converter. Okay, and this is also known as the PAM signal, pulse amplitude modulation signal. Okay, which has different levels of signals. Okay, we have 4 different levels. Okay, and then what? Then, okay, we have 4 different levels of voltage, and we put inside the product modulator. So both I channel and Q channel has product modulator. Product modulator will multiply the input. Okay, for I channel, okay, for I channel, the product modulator will multiply the input of PAM signal with sine wave for I channel. This is a I channel. Okay. For Q channel, the product modulator will multiply the input with cos omega ct. Okay, so this is a phase shifter, 90-degree phase shift. So 90-degree phase shift of sine will be cosine. Okay, perubahan 90 darjah kepada sine wave menghasilkan cosine wave. Okay, so the the Q channel will use a cosine function. Okay, so that means you're gonna produce 4 different output at the product modulator. So you see that here, that means for the I channel, for example, for the I channel, we're gonna have negative 0.541 from this table. So from this table, I will show you. So we have 0.541 sine omega ct. So everything is multiplied with sine. Okay, negative 1.307307 sine omega ct. And another one is 0.541 sine. Another one is 1.307307 sine omega ct. So there are 4 possible output of the product modulator in the I channel. Similar with the output of product modulator in the Q channel, where we multiplied with cosine. Okay, so that means it's gonna be negative 0.541. So negative 0.541 cos omega ct. Another one is negative 1.307 cos omega ct. 0.541 cos omega ct. This is 1.307 cos omega ct. So we have 4 possible output of product modulator in the Q channel as well. Okay, and then what? It's gonna put inside the linear summer. So linear summer will sum up both of it. So we're gonna produce x sine and also cos. Okay, x sine and cos. So the output of linear summer gonna be x sine omega ct plus minus y cos omega ct. Okay, and then put inside the band pass filter to select the certain frequency, and then we're gonna produce output as a 8 Qualm. Okay, so let's see what is the example. So this is the example. Okay, because we're gonna have up to 8 symbols. So what I will show you is up to 4 symbols. Okay, so I think I have put this in the notes. I hope that you can find this in the lecture notes. Okay, so this is actually what will be asked in the quiz. So I think in the quiz we also will ask these kind of questions. Given the input, what is the output? Okay, so for example, remember 8 Qualm, that means we have 8 possibilities of input. Okay, either 0, 0, 0, 0, 0, 1. So I'm trying to explain as detailed as possible for you. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so you see that we have 8 possibilities of input. Okay, so we so this is a QIC bit. QIC bit. Okay, so let's do from the beginning. Okay, let's do from the beginning for input 0, 0 and 0. That means Q0, I0 and C0. Okay, so for 0 and 0, according to the table, 0 and 0 will produce negative 0.541, and then we multiplied with the product modulator with sine for the I channel and cosine for the Q channel. So we're going to produce this one. For I channel, we will produce negative 0.541 sine omega ct. Okay, and for the Q channel, 0 and 0, which is this one, the first one, will produce negative 0.541, and in the Q channel we multiplied with cosine, so we're going to produce this one, negative 0.541 cos omega ct. Okay, and we put inside the linear summer to sum up both of these, sine and cos. Okay, it become like this, negative 0.541 cos omega ct minus 0.541 sine omega ct. Okay, so if you see from here, this is located in the third quadrant. How do I know that? Okay, how do I know that? So remember the quadrant diagram. Maybe I can refresh again what we have seen previously. The quadrant diagram, this one. You see that maybe I can erase this one. I can erase this one. Okay, so from the quadrant diagram, you see that here positive sign is located on the right side. Okay, positive sign is located on the right side. Okay, and negative sign is located on the left side. Okay, and then if you see positive cos is for the above quadrant, quadrant 1 and 2. Negative cos would be quadrant 3 and 4 below. Okay, negative cos, positive cos. Okay, and then here is positive sign, negative sign. Okay, so since this is negative sign and negative cos, remember negative sign and negative cos, so that means it is located at the third quadrant. Okay, 1, 2, 3, 4. Okay, so negative sign on the left, negative cos below, so it is located at third quadrant. Okay, so I go back to the slide. Okay, so this is located at the first quadrant, second quadrant, third quadrant, fourth quadrant. Okay, so remember this is sine, negative sine, cos, negative cos. Okay, so it is actually located at the third quadrant because this is minus sine and minus cos. Okay, so we want to simplify the equation. Okay, we want to simplify the equation. What we do is that we try to find the magnitude and also the phase in order to simplify the equation. Okay, so the magnitude is square root of 0.541 square plus 0.541 square. So we get the magnitude of this equation is 0.765. Okay, and then the phase theta. Okay, the phase theta is, we're gonna find this arctangent. Arctangent is shift tangent. If you use a calculator, it is shift tangent Okay, shift tangent of minus 0.541 over minus 0.541. So that means, so you need to change your calculator mode into degree. Okay, tukar kepada degree. So if you see a shift tan of 1, you're gonna get 45 degree. Okay, but remember, this 45 degree is actually 45 degree from the x-axis. That means, maybe I will erase this one. So 45 degree that we get is actually over here. Okay, 45 degree from that point. It is actually 180 minus 45 degrees. So if we want to based on the trigo, if we want to calculate based from this angle, okay, from this angle, it is actually 45. It is actually 45 degree. Okay, 40. Sorry. So 45 degree minus 180 degree. So it is negative 135 degree from this angle. Okay. So if we are using a clockwise degree, it is a negative. Normally we use a anti-clockwise. Okay. If it is an anti-clockwise, it is a positive degree. So this is mathematics. So if it is a clockwise, that means it is a negative 135 degree. Okay. So negative 135 degree for the phase, and the magnitude is 0.765. From here, we can simplify the equation to become like this. 0.765 from the magnitude sine omega ct minus 135 degree. Okay, so we can simplify the equation using sine function. Okay, using sine function only with the magnitude and the phase difference. Okay, so 0.765 sine omega ct minus 135. So this is the first input. Okay. So if you have question, please ask. Okay, if you have question, please ask. Okay. If not, I will move to the next input. Okay. So let's look at the next input is 010. Okay, sorry, 001. Okay, so we have seen a 000. The next is 001. 001 means that Q0, I0, and C is equal to 1. Okay, so in I channel, it's gonna be 0 and 1. So 0 and 1, if you see from the truth table, is gonna be the second row. The output of the level converter is positive 1.307. Okay, so therefore in the I channel, okay, in the I channel is gonna be minus 1.307 multiplied with sine function. So the output of the level converter, the output of the product modulator, gonna be negative 1.307 sine omega ct. Okay, for the Q channel, quadrature channel, 0 and 1, again we are using the second row of the level converter table, okay, which is negative 1.307. So Q channel, we multiplied with cos omega ct in the product product modulator, and then here is produce the negative 1.307 cos omega ct. And if we rearrange the equations, the output of the linear summer would be, we sum up both of these, I channel and Q channel. So negative 1.307 cos omega ct minus 1.307 sine omega ct. Okay, so from here you see that it is minus and minus, minus cos and also minus sine. Again, this is located at the third quadrant. Okay, this is located at the third quadrant because this is minus cos and minus sine. So it is located at the third quadrant. Okay, the third quadrant. Okay, so I need to simplify the equation as a sine function only. So therefore I need to find the magnitude 1.307 square plus 1.307 square, and then put square root, and then I get 1.848 volt. And the phase would be arctangent of negative 1.307 over negative 1.307, which is 1. So arctangent of 1, you're going to get 45 degrees. So remember, you need to change your calculator mode into degree so that you can get the 45 degree. Okay, again, so this is 45 degree at the third quadrant. So that means this is 45 minus 180 degree. So it is actually minus 135 degree. Okay, if we from the x-axis clockwise, from the clockwise point, it is a minus 135 degree. Okay, clockwise. So therefore, for 001 input, we're gonna produce output which is 1.848 sine omega ct minus 135. Okay, so based on this, both of these input, you see that for the same degree of angle, there's a two different levels of amplitude. Okay, untuk degree yang sama ini, minus 135 degree, we have two possibility of output. The first one is 0.765. The second one is 1.848. Okay, and if you see from both of these, okay, I want to show you about the first two input. The first two input, which is this one. The first two input from the truth table. Okay, we're gonna produce the output first input at 0, 0, 0. So we have the amplitude 0.765. Angle phase is negative 135. For the second input 001, we're going to produce output with amplitude 1.848 and the phase is negative 135. And if you see from this phasor diagram, what happened? So we are producing the first input, which is 0, 0, 0, which is the angle is 135 degree, and the amplitude is 0.765. And the second input, 001 input, we produce the output again at negative 135 degree, but different amplitude, which is 1.848. So you see that from here, we learn that each of the phase difference produce two different levels of amplitude. So this is what we call as Qualm. There's a phase changes and there's the amplitude changes. Okay, and if we see the phasor diagram, you see that we have the first symbol 0, 0, 0, Okay, 0 0 0. So this is a dot over here. So this is actually, if we use this is 135. Okay, 135 degree, 135 degree. And another one, second input, okay, which is minus 135 degree, but further away, different in terms of amplitude. Okay, so this is 0.7 amplitudes. Another one is 1.848 volt amplitude. So this is just for two input. Okay, so let's continue with the third and fourth. Okay, so that you can have more understanding. Okay, because there might be a possibility that we will ask this in the quiz. Okay, given the input, how much is the output? Very simple. Okay, very simple. So I already give you the answer. Okay, I already give you the answer for the quiz. Okay, so if you see the third input, okay, let's go. If you don't understand, please ask me question. Okay, for the third input, remember third input is 0 1 0. Okay, 0 1 0. 0 1 0. That means Q0 I equal to 1 and C equal to 0. For the I channel, okay, I channel, 1 and 0. 1 and 0 is, if you see from the level converter table, which is the third row, it will produce positive 0.541. Okay, 0.541. And since it is a I channel, we multiplied with sine function. So the output of the product modulator would be 0.541 sine omega ct. And for the Q channel, 0 and 1. Okay, if you see the Q channel, 0 and 0. So 0 and 0, that means we need to see from the level converter table, truth table, it is actually the first row which produce negative 0.541. Okay, so level converter produce negative 0.541. Then we multiplied with the cos omega ct in the product modulator. So we produce negative 0.541 cos omega ct. Okay, so this is actually located at the fourth quadrant, because this is positive sine and negative cos. Okay, positive sine. So this is sine, positive, negative sine. This is cos, negative cos. Okay, so positive sine and negative cos, it is located somewhere in the fourth quadrant. First, second, third, fourth quadrant. Okay, so I want to simplify the equation sine and cos to become sine function only. So I need to find the magnitude, which is square root of minus 0.541 square plus 0.541 square. So I produce 0.765 volt. And the phase is going to be arctangent of 0.541 over minus 0.541, which is negative 1. So arctangent of minus 1 produce negative 45 degree. So negative 45 degree is actually over here. Okay, okay, negative 45 degree, but the amplitude is 0.765. Okay, so therefore the output produced by the linear summer gonna be 0.765 sine omega ct minus 45 degree. Okay, which is somewhere over here. Okay, the amplitude is 0.765. Okay, this is for the third input. For the fourth input, which is 0.11. Okay, so 0, 0, 1, 1, that means Q0, I1, C1, C bit equal to 1. And if you see from the level converter, 2 to 4 level converter, for I channel, okay, which is 1 and 1, you're going to see the fourth row, it's going to produce positive 1.307 volt at the output. And this, in the I channel, we multiplied with a sine function. So the output of the product modulator would be plus 1.307 sine omega ct. Whereas for the Q channel, okay, Q channel would be 0 and 1. So 0 and 1, if you see the output of level converter would be the second row. It will produce negative 1.307, and then we multiplied with cos function in the product modulator, and it will produce negative 1.307. And if we see from here, it's going to be 1.307 sine omega ct minus 1.307 cos omega ct. Again, this is plus sine and also minus cos. This is located at the fourth quadrant as well. Okay, now I want to simplify the equation to become sine function only. So I need to find the magnitude. Square root of 1.307 square plus 1.307 square, I get 1.848. And then what about the phase? Would be theta would be arctangent of 1.307 over negative 1.307. So I get this one, arctangent of minus 1. So you get minus 45 degree. Again, the same 45 degree. And we can produce the output, simplify the output as a sine function, which is 1.848 sine omega ct minus 45. So the amplitude here gonna be 1.848. So 1.848 would be somewhere here. Okay, 1.848. And the angle would be negative 45 degree. Okay, so you see that this is for 0, 0, 1, 0 input and also 0, 1, 1 input. And if you want to see the diagram, you see that the truth table, we produce the third and fourth input. Okay, 0.765 volt minus 45 and also 1.848 minus 45. So this is actually located, if you see the phasor diagram over here, for the third input 0.10, so this is minus 45. Okay, and for the fourth input over here, because it is a different in term of amplitude, so this is in term of amplitude 0.765. In term of amplitude this is 1.848. Okay, similar with the constellation diagram on the right, C diagram, constellation, so this is 0.10. Again, this is 45 degree. Okay, minus 45 degree. And another one is here for the fourth input, 0.11. Okay, so I already shown you up to 4 inputs. The rest you can try on your own. Okay, yang lain boleh cuba sendiri. Okay, so make sure in your notes you can find these notes, additional notes that I put inside the lecture notes. Okay. So before we proceed, anybody wants to ask questions, you are most welcome to ask question. Okay. Ada soalan boleh tanya. Is there any question? No question? If there's no questions, I will move to the next next topic. Okay, kalau tak ada soalan, saya akan teruskan. Okay, if you have question, please ask question now. If not, I will move to the next topic, to the next slide. Okay, kalau ada soalan, dipersilakan untuk tanya. Kalau tak ada, saya teruskan. Okay, so no questions. Then I will move to the next slide, which is this one. So this is, I just go through it. So this is a 16 QAM. Okay, 16 QAM, I just go through this one because we might not ask this in the quiz. Okay, I just go through so that maybe you can have a roughly get some understanding about this. 16 QAM means that we have 4 input bit. Okay, 4 input bit. So 4 input bit will be split into I channel and also the Q channel. So the bit would be split to Q, Q prime, I and I prime. Okay, so Q and Q prime will go to the Q channel. I and I prime will go to the I channel, in phase channel. Okay, and then based on the level converter, it will produce a pump signal which has 4 different variations of output voltage. Okay, 4 different variation of output voltage. Again, put inside the balanced modulator, we'll do the multiplications. Okay, so in the I channel, we multiplied with sine function. In the Q channel, we multiplied with cosine function. And then put inside here, that means we're going to have 4 different output at the output of balanced modulator, which is x sine omega ct. Over here, we're going to have y cos omega ct. And then the output of a linear summer, we're going to have x sine omega ct plus minus y cos omega ct. Okay, and then we can simplify the equations to become z sine. So we can simplify the equation at the output as a function of sine. Okay, so we can produce z sine omega ct plus minus theta. Okay, the difference of in terms of amplitude and also the difference in terms of theta or phase. So since if we use 16 QAM, okay, ini adalah 16 QAM. So for 16 QAM, that means we have 16 different symbols. So if you see the diagram, it's going to be like this. Okay, it's going to be like this. So we have 16 different symbols with different amplitude and phase. Okay, and from the table, we can produce the Phasor diagram. You see that there's a lot of symbols over here. Okay, so we're going to produce 4 symbols in each of the quadrant. Okay, so this is the Phasor diagram and also the constellation diagram. You see that we have 4 symbols in each of the quadrants. So if you go to a high level of modulations, you're going to see that the dot symbols will be very close to one another. And from here, you're going to see that the symbols are close to another. And compared to the binary phase shift keying, these 16 QAM are more prone to the error, because the symbol is very close to one another. Okay, and the good thing is that we can have a high speed of transmission. Okay, we can have a high speed of transmission. And QAM also, of course, we need a bigger bandwidth compared to BPSK. But the thing is, we can accommodate many inputs. That's a good thing. Okay, so these are when we if you see from the practical applications in the 4G and 5G applications, we still use QAM. Okay, high level QAM, 64 and above, 64 and above QAM for the 4G and 5G system, telecommunications. Okay, so you know that QAM, this QAM has again in terms of speed, in terms of capacity, we can support many users. In terms of bandwidth, although it is big, but it is not too big, because QAM also reduce the bandwidth consumptions because we are applying different levels of amplitudes. Okay, so that's all for chapter 4. For chapter 4. Can I get your response? Are you still there? Adakah kamu masih ada di sana?
Yes, betul.
Okay, thank you for the response. So, do you have questions or not? If there's no questions, I want to explain about the project. Okay, I want to explain about the project. Any questions? So, any question can ask. Otherwise, we can see the project task. Okay. 1, 2, 3. Okay, no questions. I hope that you can understand this. Again, you can see this lecture video later in the YouTube to repeat again what I have explained to you. Okay, so hope that you can understand. Okay, so since there's no questions, so I will close this and open the. Okay, I will open the. Wait. Okay, so I will close this and okay, can you see my screen?
Yes, Doctor.
Okay, thank you for the response. Okay, so this is a second task. I have given this in the WhatsApp, and I will put this also in the author. I hope that you already received this document. Saya harap kamu sudah terima dokumen ini melalui WhatsApp. Saya dah bagi rasanya. Wait, yes. So I already gave you the second task on 2nd June. Okay, so in the WhatsApp, you can check in the WhatsApp. So this is about digital modulations and transmission chapter 4. This is about PCM. Okay, and the duration is about 5 weeks. So you can submit during the study week. And if you can complete as soon as possible, will be better. Okay. So I jump to the instructions. Okay, this is same as task 1. So this is about the groupings and so on. Again, you will produce 2 things, which is report and also the video presentation. Similar with task 1. So the output of task 2, you're going to produce group report and also group presentation recorded video. Okay, so what you will do actually, okay, what you will do, okay, this one. So this is about pulse code modulation, PCM. which involve sampling, quantization, and also the encoding. Okay, so for the second PBL activity requires depth knowledge of pulse code modulation in chapter 4 to analyze the complex problem of analog to digital conversions and digital signal transmission. Okay, students are given a range of technical specification and limitation for analog modulation signal, sampling rate and sampling bit for PCM encoding and decoding system. Students need to analyze the resulting PCM signal characteristics under different scenarios and propose a solution to recover the modulating signal from the decoded PCM in the receiver system. Okay, so actually there's involved generating the PCM signal. Okay, in order to generate the PCM signal, we need to do the sampling, we need to do the quantization, and then we need to do the encoding process, the formatting process, okay, that you have learned in chapter 4. Okay, students need to form small groups, again using the same group. I hope that you are good with your group members. Okay, each member allocated individual responsibilities or portfolios to complete the given task within specific timeline. No budget is allocated for the PBL project. No specific labs workshop are scheduled. Groups must manage their schedule and their own resources requirement. Okay. These PBL activities involve group discussions on the wide ranging of technical requirements to recover the modulating signal by proposing the suitable solution that would produce same analog modulating signal at the receiver output. So it involves transmitter and receiver part. You produce PCM, and from the PCM received at the receiver, you want to produce the original signal. Okay. At the end of this PBL activity, each group of students needs to submit a technical report and recorded video presentation of the proposed problem solutions. Okay, so given the trigger statement, pulse code modulator circuits digitizes the given analog signal, codes it and samples it, and then transmit it in the analog form. This whole process is repeated in a reverse pattern to obtain the original signal at the receiver. However, the encoding and decoding process must meet a certain crucial requirements, including sampling frequency, quantization intervals, voltage range, and allowable amplitude modulation in certain range. Okay, so this task 2 requires you to use a MATLAB. Okay, I hope that you can find the MATLAB. You can download the MATLAB from the MathWorks website for free using your student account. You can register MathWorks using your UTHM account, and you can download for free the MATLAB. Okay, so now Figure 1 shows the block diagram to encode and decode an analog modulating signal MT using pulse code modulation technique in digital transmission. You are given different scenarios to analyze and discuss the resultant recovered modulating signal M prime T, which is the output at the receiver. So there's a transmitter and also the receiver. Okay, so this is the suggested block diagram. We already gave you the block diagram to guide you to solve the task. If you want to add more blocks, it's up to you. Okay, ini adalah blok cadangan. Okay, you can use this to produce the output, no problem. If you want to add more to the blocks, it's up to you. Okay, so the input is given. Okay, 2.5 sine 1000 pi t. Okay, so now again, I repeat again, this is involve transmitter and receiver parts. Okay, we want to see what is the output of the transmitter, and we want to see what is the output of the receiver. So you need to analyze the things that we transmit, and also the output that we received from the output of the receiver. That's the final answer. Okay, there's a few scenarios that you need to analyze. Okay, the first part A is when you're sampling at different scenarios. Okay, so for example, you sample at 2 FM but using different bit for encoding. Scenario 1, you sample at 2 FM but using 4 bit of encoder. Scenario 2, you sample at 2 FM but using 8 bit of encoder. So the difference is in terms of number of bit. This is for part A. That means sampling the minimum you are sampling at the minimum Nyquist rate. Okay, and for part B, you are sampling more than the minimum Nyquist rate. You are sampling more than 2 FM. Okay, students, define your own value. Again, the frequency is up to you. You can decide. Okay, you can decide the frequencies, and must be more than 2 FM, but different in terms of number of bit. So we want to see the output. We want to see what is the output of the transmitter and what is the output of the receiver. Okay, so you need to check the output of the simulation. Okay, that's part B. And part C, we want to see what happens if we sample less than 2 FM. What happened? Okay, so we are sampling less than 2 FM using 4 bit. So what is the output of transmitter and what is the output of the receiver? Okay, kali ini kita nak lihat macam mana apa yang berlaku kepada signal kalau kita sample kurang daripada Nyquist rate. Okay, and then what? From part A, part B, part C, compare and discuss the results. Explain the parameters that influence the quality of the recovered message. So you need to compare part A, B, and C. What have you learned from this part A, B, and C? Okay, so have a discussion. Make sure when you explain, please explain in details. Okay, because your explanation reflects how you understand the output actually. Okay, please explain what can you describe from the part A, B, and C. Okay, and then part D. Okay, part D, with initial setting from part B are remained, what will happen to the recovered message M prime T if the amplitude of input message is changed to 50 volt and also 0.5 volt. From part B, you see that part B you need to sample more than 2 FM and using 4 or 8 bit. Now for part D, we are using the setting in part B, but we are changing the input MT. Okay, the input signal is changed. The amplitude of the input signal is changed to 50 volt and also 0.5. Okay, so discuss your observation at the output of sample and hold at the receiver. Sample and hold is this one. Okay, the output of sample and hold at the receiver. Okay, we want to see what happened at the, actually we want to see what happened over here at the oscilloscope. Okay, how does the output looks like in the oscilloscope? Okay, that is part D. So based on this part D, what would you suggest to make sure the recovered signal MT is same or similar to the modulating signal MT? Discuss and prove your findings. So there's a hint, you can change the setting block diagram and or add additional block diagram if necessary. So after part D, you need to make some changes. You can suggest some changes in order to get the similar signal as empty at the output of the receiver. What should you do? Okay, when you suggest, you need to do it in the simulation. Apabila kamu mencadangkan, kamu perlu buat dalam simulation. Okay, for example, we need to add this blah 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 blah. So you do it. You do the simulations and get the output and show the results. So in this part, it is not only you explain, but you need to make it. Okay, you cannot suggest something, you cannot do it. So you can find the suggestion from anywhere, from the internet, from the books. So you do it in the simulations and prove it that you can produce the same input signal at the output of the receiver. Okay, and then what? This so this is okay, again, this is the same this is the report discuss the summarize the FILA table, fact, ideas, learning issues and actions as guidance to the organized task. FILA table is the planning phase. You need to plan and then prepare the brainstorming process, providing the appropriate tools, fishbone diagram and flowcharts. Prepare the report and video presentations. So video presentations around 20 minutes to describe your works. So make sure all the group members speak during the presentation. Okay. Submission due date is 5th of July. I hope that you can finish by this date. Okay, so that I can give you marks before your final exam. Okay. And if you need more time, you can inform me. Okay, I can give you extra time if needed. But if you can finish as soon as possible, would be better. Okay. And the last one would be self-reflection. You can put inside the report. Okay, this can be put inside the report. Okay, this is one report, one self-reflection. Okay. Satu report, cuma satu self-reflection sahaja. Okay. So any question you want to ask about task number 2, boleh tanya. Any question for task number 2? No question? Or you don't have question yet? Can I get your response? Are you still there?
Don't have a question yet.
Okay. Belum ada soalan
Belum lagi.
Okay.
Belum.
Okay, if you have question, you can ask. Otherwise, you can ask later. Okay, boleh tanya dalam group. You can ask in the WhatsApp group, no problem. Okay. So, again, you need MATLAB. And you can use this block diagram. So this is the suggested block diagram. So you don't need to think again, what should I put? What should I put in the MATLAB? So this is what you should put in the MATLAB. This is a suggestion. If you want to do different from this, it's up to you. Okay, tidak ada masalah. This is just a guidance. Okay, this is a guidance for you to produce the output. Okay. So, if there's no questions, any question? Ada tak soalan? Boleh tanya Belum ada lagi? Kalau if you don't have question yet, no problem. You can ask later. So, we still, now the time is 4:24. I still have half an hour. Okay. I need to start with chapter 5. Okay, saya perlu mulakan chapter 5 walaupun sedikit although it is small little bit chapter 5, I need to start as soon as possible. You know that ECS contains a lot of topics that need to be covered, so I need to proceed. Okay, I need to proceed, but maybe before we proceed, can we have a 5 minutes break? I want to make a coffee so that we can continue again at 4:30. Okay, so let's take a break for a while. I will continue again at 4:30 with chapter 5. Okay, saya akan sambung chapter 5 pada pukul 4:30 and we're gonna stop at 5 o'clock. Okay, so let's take a break 5 minutes. Okay, see you again 4:30. Okay. Okay, can we start now? Are you still there?
Yes, Doctor.
Okay, thank you for the response. I hope that you already take your 5 minutes break. So I managed to make a coffee. Okay, and I will proceed for another half an hour with chapter 5, the last chapter. Okay, the last chapter. So for some of you that might be fall asleep, okay, I hope that you can wake up between 4:45 until 5 p.m. Okay, we're gonna take the attendance. Okay, so mungkin ada yang tertidur, harap yang tertidur tu boleh bangun antara 4:45 sehingga pukul 5 because we're gonna take the attendance. You might be surprised that among your friends there's some of you that fall asleep at the end of the class, so they forgot to take the attendance. Okay. Okay, let's proceed with chapter 5, transmission line, antenna, and wave propagation. So this is the last chapter, which consists of 3 topics: transmission line, antenna, and wave propagation. And for your information, this chapter is consists of topics from 3 different subjects. Okay, we have 3 different subjects that covered chapter 5. So chapter 5, we compress it, we summarize it from 3 subjects into 1 chapter. Okay, so transmission line, you will learn more in the EMC subject, electromagnetic compatibility subject. We have antenna subject for the communication students. And we have the wireless and mobile communication subject for the communication students as well. Okay, so for communication students, they will learn more about these topics in the next subjects. Okay, and if you see again, so what we will learn here, again, I will draw this picture. The transmitter, okay, we have the channel, we have the receiver, okay. So from chapter 1 until chapter 4, we have seen what happened inside the transmitter and the receiver. Now in chapter 5, we are not looking inside the system. We are looking from the outside of the system, so which consists of 3 different things. The first one is a transmission line. So transmission line, if you see that transmission line is the medium. Either the medium is wired, okay, this is a wired medium, okay, or the wired medium that connected to the receiver. Okay, so this is the wired medium and can also be a wireless medium. So we are learning about the medium of transmission, the first topic. The second topic is the antenna. Antenna radiates the received signal into electromagnetic waves. Okay, and at the receiver it will absorb the transmitted signals and send it to the receiver to recover the signal. The last topic is the wave propagations. Is about the characteristic of the wave propagation. Okay, the characteristic of the waves that propagates in the medium. That's the third topic. Okay, and chapter 5, again we will divide into 3 different topics, which is the transmission lines, antenna, and wave propagation. So we're going to go through this one by one. So there's going to be, in the final exam, there's going to be question about this and also the last topic. Okay, So the last topic, wave propagation, would be the favorite question that always come out in the final exam. So if you try to do the previous semester's final exam for the wave propagation topics, I believe you can answer the final exam, no problem. Okay, we normally recycle the questions. Okay, we just change a little bit so that you can score the final exam. Okay, if you study. If you are not study, it's gonna be difficult for you. Okay, so the type of waves, there are two type of waves, water wave and electromagnetic waves. Okay, so you see that the water wave in the picture, given in the picture, and electromagnetic waves given in this picture for electromagnetic waves. So water wave and electromagnetic waves are categorized as the transverse wave. Okay, transverse wave. So transverse wave means that the wave oscillate in the direction of the propagation. Okay, when it moves into a certain directions, it also propagates at different angle. That's a transverse wave. Another one is what we call as a longitudinal wave. So the wave, for example, for longitudinal wave is sound wave, which is constituted of compression and decompression of air. So this is longitudinal wave. So we're gonna learn a lot about this wave, electromagnetic waves. Electromagnetic waves consist of electric field and also the magnetic field, both of it. And if you see transverse wave, transverse wave is a moving wave that consists of oscillation occurring perpendicular to the direction of transfer. So that means if the wave moving from left to right, it will oscillate, for example, up and down, which is 90 degrees from the angle of movement. So it is move in one direction, and at 90 degrees of the movement directions, it will oscillate. Dia akan berayun. That is what we call as the transverse wave. Okay, so this is also for the electromagnetic waves. So transverse waves, there are four possible types. The first one is transverse electromagnetic mode, known as the TEM mode, and then transverse electric TE mode, where there is no electric field in the direction of propagations. Transverse magnetic TM mode, where there is no magnetic field in the direction of propagation. And another one is what we call as the hybrid modes, where there is non-zero electric and magnetic fields in the direction of propagation. Okay, so we're gonna the electronic communication system, for the wireless system, we normally use the TEM modes, okay, for the wireless propagation. TE and TM modes is for the communication using the waveguide, which is this one. Okay, so for TE and TEM modes, it is only possible for the through the waveguide. So waveguide is a hollow metallic connector that connect transmitter and the receiver. Okay, it's a hollow metallic conductor that connects transmitter and the receiver. Normally it is a short distance. So transmission through the waveguide, normally for the high frequency transmission. Okay, normally for the high frequency transmission in the form of gigahertz of transmission. Okay, in a short distance, we are using the waveguide. Okay, it is you can search in the internet how does the waveguide looks like. So there are many design of waveguides, but the material will be the hollow metallic. Okay, it is a hollow metallic conductor. So transverse electromagnetic, for TAM modes, so TAM modes, propagation of electrical power along the transmission occurs in the form of transverse electromagnet. A TAM wave propagates primarily in the non-conductor dielectric that separates the two conductors of the transmission line. E and H, E field, electric field and magnetic fields are perpendicular to each other, which is what also known as a space quadrature. So electric field and magnetic field are perpendicular to each other. Okay, dia adalah bersetentang antara electric field dan magnetic field adalah bersetentang antara satu sama lain. So TAM mode is not possible inside the waveguide, so it is more suitable in the wireless and copper wire. Okay. So we're going to see more about the transverse electromagnet. Okay. And if you see from here, this is the picture of transverse electromagnet. This shows the electromagnetic fields that move into these directions. Okay. And it oscillates at 90 degrees of angle. And if you see, the orange color is the electric field and the blue color is the magnetic field. So both of these, E field and electric fields, are perpendicular to each other. So they are oscillating at 90 degrees angles and then moving into different angle. So this is what we call as a TAM waves, which is electromagnetic waves. Okay, the electric field perpendicular to the magnetic fields and it moves into different angle. Okay. And wave velocity, the speed of the wave. Okay, so the speed of the wave is depending on the type of medium. Okay, in the free space or in the vacuum, the electromagnetic wave travel at the speed of light, which is 2.998 times 10 power of 8, or we normally use 3 times 10 power of 8 for the speed of light. Okay, but if the medium is non-vacuum, okay, the wave will travel slower, a little bit slower, okay, compared to the speed of light. And the wave velocity parameter is equal to velocity factor multiplied with speed of light. Okay, so this VF is from the range of 0 point something until the maximum would be 1.0. Okay, so if the medium is non-vacuum, so the velocity factor will be reduced less than 1. So you get the speed less than speed of light. Okay, so VF, velocity factor, is depending on the type of medium. Okay. Frequency and wavelength. So wavelength, lambda, is the length of one complete oscillation of the transverse wave, lambda. Lambda shows how long does the wave has traveled in one complete cycle. Okay, berapa jauh gelombang itu telah bergerak dalam masa satu kitaran lengkap. The unit would be in meter. Okay, so lambda is equal to velocity. Velocity is in terms of meter per second multiplied with second for time. So you're going to get lambda in terms of meter. Okay, lambda in terms of meter. Okay, and for the frequency is the rate of change which the oscillating wave repeats itself. Okay, frequency is equal to 1 over t. Okay, so lambda is equal to v over f. So we normally known about this equation. Lambda is equal to v over f. So if it is in free space in the vacuum, that means the velocity would be the speed of light. Okay, if it is in free space, that means the velocity will be speed of light. You divide with the frequency, so you can get the lambda in terms of meter. Okay, so if you see from here, the higher the frequency that you used, the smaller would be the lambda. Okay, lagi besar frekuensi, lagi kecil nilai panjang gelombang. Okay, that means in high frequency, the wave can travel at short distance only in one complete cycle. So we are talking about one complete cycle. Okay, so in one complete cycle, the wave only travel at short distance. Compared to if we use a low frequency, okay, we're gonna have higher lambda. That means the wave can travel at longer distance within one complete cycle. Okay, so this is about the lambda. Okay, you can calculate the lambda. Remember, the lambda is only measured within one complete cycle. For example, sine wave, you start with at 0, so you're going to stop here at one complete cycle, and then the next cycle. So this is actually another lambda. Okay, this is actually another lambda. And if you start at t over 4, okay, you stop at after t over 4, so you're going to get one lambda, and then there's another lambda over here. Okay, 1 lambda, 2 lambda, 3 lambda, and so on. So the distance of movement is measured in terms of lambda, 1 lambda, 2 lambda, 3 lambda, and so on. Okay, so transmission line can be categorized either guided or unguided. So guided means that the wave is guided from one place to another. So guided is referring to the wired transmission, whereas for unguided means that the wave is not guided from one place to another. Okay, that means this is referring to the wireless medium. Okay, so for guided transmission, okay, for example, it is like a copper wire or optical fiber. Unguided transmission is a wireless medium without any physical conductor. Okay, for example, the free space or the air. Okay, and the direction of propagation is unguided, means that the wave can travel in many directions. Okay, guided transmission for the wired medium, it can be categorized into 3 categories, okay, which are the balanced transmission, unbalanced transmission, and also the balloon. Balloon is a combination of balance and unbalanced. Okay, balloon is actually is the transmission line to connect balance and also the unbalanced transmission line. Okay, balloon is used to connect both of it, balance and unbalanced. So balanced transmission line consists of a 2-wire transmission line where both conductor carries the current. So one conductor carries the signal while the other conductor carries the return path. So this type of transmission is called differential or balanced transmission lines. So if you see, this is a balanced transmission line consists of 2 wires like this. Okay, so this is a balanced transmission line. So this is also balanced transmission line. This is also balanced transmission line using unshielded twisted pair. So the twist pattern result in reduction in the electromagnetic interference, EMI, and radio frequency interference. Twisting also reduce crosstalk between the cable pairs. So that's why you see there are many cables that we twist the cables. So there's a purpose for that. It's not only for fancy. So there's a purpose to twist the cable so that we can reduce the interference. Okay. Shielded twisted pair. So this is also balanced transmission line, consists of 2 wires. Okay, so it has a shielded. Here is we have shield the cable with the material to protect it from the from the interference, okay, from the noise crosstalk, okay. So this is a shielded, we have the outer shield of the cable, okay. And for the unbalanced transmission lines, for example, like the coaxial cable, okay, so it has a, for unbalanced transmission line is a one wire, okay, which one wire is at ground potential whereas the other is at signal potential. So unbalanced transmission line, the ground wire may also be the reference for another signal wires. Unbalanced transmission line have the advantage of requiring only one wire for each signal and only one ground line is required, no matter how many signals are grouped in one conductor. So one of the example of this unbalanced transmission line is the coaxial cable, okay. So coaxial cable, for example, this one is a coaxial cable, this is the unbalanced transmission line, okay. Another example of unbalanced transmission line, so this is a picture of unbalanced transmission line. And then we have balloon transmission line, a circuit or device used to connect the balanced transmission line to unbalanced load. This is what we call as balloon, okay, balance to unbalance. So balloon, the name balloons means that balance to unbalance. So balloon, for example, there are many types of balloon. Among the examples here are the transformer balloon, okay, which is this one, picture A. So you see that here we have input unbalance, okay, from the coaxial cable, and we want to transfer it into a two-wire output, okay, which is a balanced output. So we need the transformer balloon over here to connect the unbalanced to the balanced output, okay, it's from one wire to two wire, okay. Another one is a bazooka balloon, which is picture B, okay, to connect the unbalanced coaxial line from the input, okay. We want to connect to the balanced transmission line, okay, two-wire output. So we use the balloon over here, bazooka balloon. So of course it has a specific dimension based on the required frequencies, okay. So the design of balloon is varies depending on the application and also the frequencies that we used, okay. Transmission line electrical characteristic. So this is important. Okay. So characteristic impedance. So we there are transmission line characteristic. There are three main characteristics. The first one is the characteristic impedance, what we call as a Z0, and then velocity factor, VF. We have seen this. And then the SWR, standing wave ratio. Okay, so these are the important parameters for the transmission line. So ini adalah antara parameter penting untuk transmission line. Okay, so transmission line, we can actually define the transmission line, the cable, in terms of lump elements, which consists of resistance, inductance, conductance G, and also the capacitance. Okay, that means we can draw the transmission line, not only a single wire like that. We can represent the transmission line as the lump elements that consist of L, R, C, and G parameters. Okay, kita boleh melukis circuit transmission line dalam bentuk parameter R, L, G, and C parameters, which is what we call as the lump elements parameter. Okay, like this. Now, so this is actually a two-wire cable. Okay, two-wire parallel transmission line, which we represent the circuit in terms of R, L, G, and C parameters. So if you have a long wire, two wire, we can represent the long wire, as a repeatable sections of lump element. Okay, so you see that it is repeatable sections of lump elements, R, L, G, and C. Okay, so transmission lines, for example, like this, consist of repeatable sections of R, L, G, and C components. Okay, in the previous exam, we have asked these questions, okay, to draw the transmission line based on the lump elements. So you need to do like this drawing, R, L, G, and C components, and you repeat sections. Okay, we have asked this in the previous final exam, pernah ditanya. Okay, so it is not just we can draw a cable like this. We can represent the cable with the components R, L, G, and C. Okay, so R is the resistance, L is the inductance, C is the capacitance. Okay, and the way we want to calculate the value of R, L, G, and C can be different from different type of wires. So you don't need to memorize this, tak perlu hafal. So you don't need to memorize this. This is just to show you that the R, L, G, and C can be calculated based on the dimension, of the cable itself. Okay, based on the dimension of the cable, we can calculate the R, L, G, and C parameters. So this is one of the method to calculate the lump elements parameters based on the dimensions of the cable. Okay, there's also another method to calculate the parameters, which you will learn later. Okay, and skin effect, you see that the skin effect, so we have asked this previously about the skin effect. What is the skin effect? Okay, so skin effect is the phenomenon that happens at high frequency, where we will see that the wave travel at the surface of the conductor at high frequency. Okay, at high frequency, there's going to be a phenomenon where the wave tends to travel at the surface of the conductor and not at the core. Okay, normally we expect the wave travel at the core of the conductor, but at high frequency, the wave travel at the surface of the conductor. So that's why we call it as a skin effect, as if the wave travel at the skin of the conductor, something like that. Okay, so it is travel at the surface of the conductor, not at the core. This is what we call as a skin effect. So previously we have asked questions, briefly explain about the skin effect. Okay, it is a phenomenon at high frequency. Okay, and then the next parameter is characteristic impedance, which I will explain next week. Okay, I will explain next week. So we're gonna stop here. Okay, we're gonna stop here, and I will explain this next week. Okay, so you can open your QR code reader. Okay, you can open your QR code reader to take the attendance. Okay. Okay, you can take your attendance, and again you can go to anywhere you like. Okay, so see you again next week.
Thank you, Doctor.
Okay,
Yeah.
welcome.
Thank you, Doctor.
Okay, welcome.
Thank you.
Okay, welcome.
Thank you, Doctor.
Okay,
Thank you,
welcome.
Doctor.
Okay, welcome.
Thank you, 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 Doctor.
Welcome.
Doctor,
Yeah.
can you please
thank you,
give me
Doctor.
assistance? Because I cannot.
Thank you, Doctor.
Okay, welcome. Pardon? Apa dia? Nak tanya apa?
Can you send me manually because I cannot use my phone?
Attendance.
Yes.
Nama siapa?
Muhammad Abdul Karim.
Muhammad Abdul Karim. This one,
Yeah.
Muhammad Abdul Karim, Abdul Rahman.
Abdul Rahman, yes.
Okay, done.
Okay, thank you, Doctor.
Okay, welcome. Any more?
Doktor,
Yeah.
nama saya Gabriel. Saya tidak dapat masuk slot.
Okay, Gabriel Ruchi. Okay.
Ya, betul.
Okay, done.
Terima kasih, Doktor.
Okay, sama. Any more?
Doctor, someone write something at the checkbox.
About what? Sundus. What happened, Sundus? Okay, so Sundus. Okay, Sundus, I already take your attendance. Okay. So complete attendance. Everybody attend the class today. So that's all for today. Okay, welcome, Sundus.